Thank you for the invitation. So I will start by telling what is my general issue. So we have an algebraic variety V over Q. Say, let us think of the rationals Q, but of course everything can be formulated over number fields, although we shall see that certain questions, in certain questions, the number field may have a difference. So let us think of Q. So, and now we take a rational map, a rational function, just to P1. And the question to be discussed is how large is the image of the rational points of V inside the rational points of P1. So this is very general, very vague. So let me illustrate various aspects with examples. The simplest examples we have when the dimension of V is 1. So V is a curve. And think of V, for instance, to be a plane curve defined by polynomial equation in the plane. Say that it is irreducible, and we take F, for instance, the x-coordinate function. So what are we asking now? We are asking for which rational points for which rationals T, the equation Pty equals 0 has a rational solution. Because this would mean if the equation has a rational solution, this means that T is in the image of the map on the rational points of V. So we see that already with this example, we recover a very general Diophantine problem. The most general, if we go to several variables, it is essentially the same. This illustrates that the problem is very much related to classical Diophantine stuff. When V is a curve, let me recall that in this case, F of V of Q is called a thin set. Thing in Q, Sarah's terminology. And it's called thin, but if the degree of the map is greater than 1. So these thin sets are relevant in Hilbert irreducibility theory. So the Hilbert irreducibility theorem wants, in this context, we want to know the rationals T such that P, T, Y remains irreducible. So you see it is related. Of course, this is not the case when the equation has a rational solution if the degree in Y is greater than 1. But having a rational solution and being irreducible are related facts. So the thin sets, so we recover the thin sets as a very special case of the question that I stated in the beginning. So in this case of dimension 1, it is easy to prove that f of v of q, the image, is somewhat small. In fact, it is called thin, but thin is a definition of this kind of set, and we want to show that it is indeed small in the usual sense. And a way to prove this is with the heights, using heights. So functoriality we have the following inequality, that the height of value of f at a point, if x is a point in V of Q, or more generally also in V of Q bar, is if it is an algebraic point, then the height of the image, since f is supposed to have degree greater than 1, is at least twice the height of x plus an error term, which is by a theorem of Néron, it is at most the square root. What is important is that this is small, and so essentially f increases much the height. So if we wanted that the height of the image is less than t, then this implies that the height of x is at most 1/2 plus epsilon, the same parameter for large values of the parameter. And then counting, if we count the points in the image, they are very, very few with respect to the whole point. Counting proves that the f of the image is small. Leaves out almost all rational points. So we attain only very few rational points. And this is a very simple argument heights. When the curve has a genus greater than 0 or greater than 1, of course, we have much more by Faltings, for instance, but this is sufficient in all genera to show that the image is small. And now let us, so for V a curve, we have a quite good knowledge. And now let us go to the case which is for interest for me. By the way, these results that I will mention are joint work with Corvaia and Masser. So if the dimension is greater than 1, again, we by taking a variety defined as a hypersurface, again, we are asking for which T in Q is this solvable in Q to the R. And then we have a more general, much more difficult problem. And these sets, by the way, are important in logic, in the theory of Hilbert 10th problem. Many problems are formulated just by taking projections of sets of rational points. So anyway, the matter is absolutely much more difficult already if so take V equal P2 and F, so a rational function of two variables defined as a quotient of two polynomials, and we now have the equation is the Fountain equation when t moves in a family. So you see t is the hypothetical value of the map, and we want to solve for each value of t, we want to know whether the curve, now the fiber is a curve, and we want to know for which values of t this curve has a point. This is very difficult problem in general. We have a family of curves, and if we have no supplementary information, this is very, very difficult. Giulio Bresciani has recently studied this issue, but uses the Bombieri-Lang conjectures, which are very strong, very open, widely open conjectures. So he has a number of results, but under this strong conjecture. A nice consequence of his analysis is that he can prove with this, he can prove the following. There are no rational functions giving a bijection from q squared to q. This is a nice problem studied by several people, also famous, Tau, for instance. And there are a number of results, but this proof uses Bombieri-Lang. So to establish this is not known unconditionally. This example, however, gives the flavor of the general issues. So in dimension greater than one might try to use again heights. But here the thing fails, the previous thing fails. So we expect that the height, we expect somewhat that the height of the image is large. But how to prove this? And what does it really mean? And again, let us try to use functional reality to see the obstacles. So we have this, our map, say from P2, let us take the simplest example in dimension greater than 1. So we have the rational map F. And now we go to a blow-up. So we can't apply functoriality directly because F is not defined everywhere. So to apply functoriality, we must have a morphism. So the idea then could be to go to a blow-up. So we blow up P2 at the points where F is not defined. And after a suitable blow up, which may be complicated, but in general will be not too complicated. Anyway, after some blow up, we can make F regular. So we can obtain a map F tilde, which is essentially F, except above the points where F is not defined. Then we shall have exceptional divisors and so on, and we have a map F tilde. Now F tilde is a morphism. F tilde is a morphism, and to F tilde we may apply the functorial formulas and deduce that the height of F tilde of X, what does it mean, the factorial formula? It means that the height of F tilde is equal to the height with respect to which divisor, on the divisor F tilde star of the point at infinity of X. And now what is interesting to explore this formula is to know what kind of divisor is this pull back. And here is all the difficulty. This pullback carries exceptional divisors. The exceptional divisors that appear in the blow-up. And this, to analyze the height with respect to these divisors is very subtle. So we cannot manage in practice, and there are the Voitas conjectures. We fall immediately in the realm of Voitas conjectures. So just to, with the Voita conjecture, we can't say much, but these are widely open conjectures, similarly to the Bombieri-Lamb conjecture. So let us forget about this, but I wanted just to illustrate that the use of heights doesn't give anything if we don't use more. So now with the Corbaia and the Massa, we, by a kind of simple way, we are able to say something when V is for instance, an abelian variety. And with the help of Mordell-Lang, we prove this theorem. If F is V an abelian variety, a rational map, then F of V of Q omits infinitely many points. So we can't cover all the points, all the rationals. This seems weak, but already this result we found it necessary to use more. We can say in fact more, but for lack of time, I won't state any result more precisely. We have in fact a weak approximation for the omitted value. So we may prove that the omitted value are many, but not, we cannot prove that that most values are omitted, which is what one would expect under the Voitas conjecture on the height. Anyway, and now let me come to the last part of the talk. And an idea is to look at possible integral values. So integral values, why? Well, because if you think of F is a rational map, is a quotient of polynomials. If we are on a projective variety, we don't expect that this quotient of polynomials will be integral very often. And so it is sensible to seek integral points in the affine line and to hope that these are good candidates for values not attained by F. We don't expect that the values of F, for instance, on an abelian variety, we have a few rational points in a sense because their height grows very rapidly. And we don't expect that these points are, that the values of a rational map are integers. So let us see what we can say about integer values. So the case of, again, in dimension one, for instance, a map even of P1 to P1 we see the affine line embedded in P1, and by Siegel theorem, there can be only finitely many integral values if F has at least 3 poles. This is a very elegant result by Siegel, a consequence of his theorem of general theorem of integral points of curves. So if we have a rational function of one variable, and if there are 3 distinct poles, it may attain only finitely many integral values at rational points. And this 3 is optimal in the sense that we can find maps with only 2 poles and infinitely many integral values, and the Pell equation provides such kind of examples. Let me now go to P2, and we finish my talk by illustrating how strange kind of problems, but also very attractive, I think, one finds already in the case of P2. So we write F as a quotient of 2 polynomials. And let us say of degree each at least 2, not to fall into some. There are some simple cases, of course, when P is when Q is constant, for instance. And now let me go to the case just of quadratic polynomials. Let me take P just as a test problem, some of these squares, and Q, I take Q, for instance, x squared minus 2y squared minus 1, for instance. This choice is rather special, but there are reasons for it, and I have no time to explain. So we seek now, we seek actually integers. I want integers now, x, y, such that f of x, y is integral. Do we find such integers? And do we find infinitely many integers? To find infinitely many is not difficult. What can we do? For instance, we solve the equation x squared minus 2y squared equal 2. This has infinitely many solutions. This is a Pell type equation with infinitely many integer solutions. And of course, for these solutions, Q is 1 at these solutions, and the quotient is integer. But this is not satisfactory because these the points are not Zariski dense. The points, these points are not Zariski dense. They all lie on this curve. So we want a Zariski dense set of integral points. And we found the question much more tricky than expected. This is very special. Let me repeat this, but this kind of examples I find useful to formulate, to understand, to get the flavor of the general problem. So I want to illustrate now. I finished the last 5 minutes by illustrating how already a very special problem like this can lead into deep questions in number theory. So we want to solve now x squared minus 2y squared equal a plus 1. And so this is the value of q then qxy will be a. And then we want that this a divides x squared plus y squared, because then the value of the function is integer. So we want these conditions. And an idea to find an infinity of solutions. So we may try with an a, solve the Pell equation, and but how to guarantee that a divides x squared plus y squared? We don't know. What we can do is to take whole infinitely many solutions of the first equation, take all solutions of this, for a fixed a, and then vary the solution, keeping fixing a, varying the solution, and trying to impose the second condition. So what happens if we put theta? We find a special solution, x naught, y naught. We construct this number in the field q of, we work now in q square root of 2. And we have that the norm, I indicate the norm with this capital N, the norm of theta is a plus 1. And now we want to use that if we define zeta 1 plus the square root of 2, the norm of zeta is minus 1. So what we find? We find that the norm of theta, zeta to the 2r, for any integer r, is again a plus 1. And so our candidate solution will be the xy provided by this identity. And we want, so we define x and y by this identity, and we want that x squared plus y squared is congruent to 0 mod a. So we have, what is the gain? The gain is we have the integer r is at our disposal. So we find after some calculation that we have an exponential equation. Theta prime here is the conjugate. And we want that this is congruent to minus 2/3 mod a. And we have this exponential equation. Now, how to solve exponential equation? Here we fall in the realm of primitive roots, modulo primes, which is a subject in algebraic number theory, which started long ago. There is a famous conjecture of Martin, and it is quite a deep and difficult matter. So now my time is almost over. Let me just say that by using the prime L equals 73, and this is a prime which splits, this is congruent to 1 mod 8 and splits in q of square root of 2. And it happens that zeta is a primitive root. And by using this fact, we can solve, and zeta is a primitive root and remains a primitive root also modulo the powers of L. So, and we can use this fact and construct A among the powers of L, and we may solve the exponential equation and finally produce a Zariski-Denk set of integers such that the value of this rational function integer. But so I finish here, and you see I just commented that just is a kind of minor miracle. If we vary the prime L, we don't know if there are infinitely many primes like this. So already a very special example of this problem leads into questions that touch but are outside the present knowledge. Oh, thank you very much for the attention and the invitation.